In the last video, we stated the n-term divergent test. This result says that if we have a sequence which limit when n approaches infinity is not zero, then the associated series is not convergent. Here we can see an example of how we can use this result. We wish to classify the series associated to the sequence n over n plus 3. So we check what is the limit as n approaches infinity of n over n plus 3, and we know that this limit is 1. Then, by the n-term test, we conclude that the associated series is not convergent. So we have classified the given series as not convergent. But what if we consider now, we also want to classify the sum of 1 over n as when n is between 1 and infinity. This is the harmonic series, and we have considered it before, a couple of videos ago, and we have seen that actually, even though we have not proved it, promise we're going to prove it later, but we have seen that this is divergent. But what if we try to apply the n-term divergent test to this series? Well, we'll try to see what happens with the limit as n approaches infinity of 1 over n. And this limit is 0. So if the limit is 0, we cannot say anything about the associated series because the result says if the limit is not 0, then something happens. If the limit is 0, then the test is useless. And in this case, we know the test is useless, but at the same time we know that the sequence is divergent. But what if, okay, I'm getting a bit messy over here, but bear with me. What if we consider the sequence 1 over 2 to the power of n? Yep, this is a geometric sequence. And let's say we want to classify the associated series. We can write it like this. Well, because it's a geometric sequence and the common ratio r is 1/2, which is in absolute value less than 1, then we know that this one is convergent. If we didn't know that and we try to apply the n-term divergent test, we'll have to look at the limit of 1 over 2 to the n as n approaches infinity, and we will see that this limit is actually 0. So what's going on over here? If we get a limit that is not 0, this result helps us classify the series as not convergent. If we get a limit that is 0, the test is useless. It could be that this associated series is divergent, as it happened with the example of the harmonic series, or it could be that the associated series is convergent, as we saw with the example with the geometric series with common ratio 1 over 2. So the n-term divergent test is only useful when we look at the limit of the n-term of the sequence as n approaches infinity, and we see that that's not 0. This means that if we get a result of 0, this test is 100% useless, and the classification of the associated series can go either one way or the other. In other words, what we are saying is, for a series associated to a sequence to converge, it is necessary for the sequence to have limit 0. So it's a necessary condition. But it is not enough, because there are some sequences with a limit 0 that are not convergent, so it's not sufficient. Again, I say it one more time. For the series to have a chance to converge, the associated sequence has to have a limit 0. If it has limit 0, then we need to, see what's happening. We're going to have more tools to classify series very soon. But if the limit is not 0, then we classify the associated series as divergent, and we are done, as happened with the first of our examples. I'm leaving here 2 more examples for you to practice. I want you to apply the n-term diversion test to classify the two series that I wrote over here. Yeah, so you can pause the video and classify them now. Now I want to move on to consider some properties about convergent series that are actually quite easy to believe because they follow from similar stated properties about limits. So let's say that we have a series an and a series associated to a sequence bn, and they are convergent, both of them. And let's also say that c is a real number. Then, if we consider the series associated to the sum of the two sequences an and bn, this series is convergent. And actually, if we wish to find the value of that sum, is the result of finding the value of the sums for each of the sequences. Similar result holds if we make a new sequence by multiplying the value c by the sequence an, and then we try to sum that new sequence. Again, we obtain a series that is convergent, and if we wish to find what is the sum of that convergent sequence, we can find it as c times whatever the sum of the sequence an was. So I believe these are easy to believe properties, and we're gonna see some examples that are using, well, everything we know about series so far. And yeah, let's see how it goes. So these are the series that we wish to classify as convergent or divergent. And for those who are convergent, we want to also find its sum. First example we have over here, we are summing from 0 to infinity 7 to the power of n over 2 to the power of 3n. We want to check what are the first few terms of the associated sequence, so we call it un. u1 is just 1 when n is equal to 0. u2 is 7 over 2 to the 3, so 7 over 8. Next term is 7 squared, and then we're going to have 2 to the 3 to the 2, so 8 squared. So you may be already seeing what's going on over here. Actually, un, we could write it as 7 over 2 to the power of 3, all of that to the power of n. So 7/8 to the power of n. So this is actually a geometric sequence. The common ratio r is 7 over 8. So the common ratio is less than 1. And the first term, we wrote it over there, is 1. So we can find the sum. We know how to do this. We need to do the first term over 1 minus the common ratio. Well, I should say, first of all, it converges. Yeah, it's a geometric series. It's a geometric sequence with the common ratio in absolute value less than 1. So the associated series is a geometric series that is convergent, and the sum, as we see over here, is 8. Let's move on to the next example. In this case, we are going to look at the limit as n approaches infinity of the general term of the sequence, so n over square root of n plus 3. And we can easily check that this limit is actually 1. The numerator is behaving like n, and the denominator is also behaving like n, as n is really big. Then by the n-term divergent test, we know that the associated series is divergent. Next example, we are looking at the sum from 0 to infinity of e to the power of minus n. E to the power of minus n, this is e to the minus 1 to the power of n. And e to the minus 1, well, that's 1 over e. This is positive and less than 1. So actually what we have here is a geometric sequence with common ratio less than 1, so this is convergent. To find the sum, we want to also write down what is the first term of the sequence, of e to the power of 0, and that is 1. So the sum of this convergent series is 1 over 1 minus e to the minus 1. But we don't need to simplify this, we can read it like that. For the last series, we have to classify over here. Again, we're going to look at what is the limit of the associated sequence when n approaches infinity. Well, 1 over n approaches 0, and then if we try to do the logarithm of terms that are approaching 0, this is going to approach minus infinity. We know, of course, the behavior of the natural logarithm function. So this is not 0. The limit of this sequence is not 0. Then again, we can apply the nth term divergent test, and then we conclude that this series is divergent.